MFP is a graphical patching system that lets you write programs by making diagrams. Sometimes you just want to write code. In this video, I'll show you some ways you can escape from the patching metaphor in MFP and write code in a more traditional style. So let's say you have a number called x and a number called y, and you want to compute the magnitude of the vector that they form together. So this is a very simple computation. It's just square root of x squared plus y squared, but it can be a little bit tricky to formulate it in data flow style. Okay, so if we take 3 and 4 and compute that, then we get 5, right? So that's what we expect. But now because we have access to Python data types in MFP, we can use a complex data type and the abs operator. That's a little bit simpler. Let me just show you how that would work. But this doesn't need any custom code. For the sake of this video, let's look at a couple more ways we can do this that let us work with custom code directly. The first method is the func built-in. Func is just a thin wrapper around Python's lambda. It lets you write a single Python expression that is applied to the processor's inputs. So the syntax is exactly like Python's lambda, except the keyword is func instead of lambda. So to find the magnitude of the vector xy, it's just x times x plus y times y to the 0.5 power, right? So the parameters of the lambda, x and y, get pulled out into inputs to the processor. Marshalling works just like a regular processor, so the leftmost hot input is what kicks off the process. And so if we connect this up, we can see that down here we compute the same value in a different way. So like any lambda, the code in a func is limited to being a single Python expression. I think these func objects are the most useful in cases like this where there's a mathematical function that we want to compute that would be a little awkward to express in a data flow style. If you want to have more complex Python code associated with your objects, or create completely new processor types, that's possible too. So let's say we want an MFP processor called vmag, which doesn't exist. It's going to compute the vector magnitude. We want it to do the same thing as this func example, but also like log its input and output or do whatever else. So if we just create a processor called vmag, it gives us an error because there's no vmag built in and there's no function in Python called vmag. But every patch element has a parameter called custom code, which is, you can find it under the params tab here in the right side info panel. Custom code is a chunk of Python which gets evaluated just before creation of the guts of the object, and any definitions in the code are available to that object, but not to any other objects. So we type in a definition for the vmag function, which takes two arguments, x and y. It logs the arguments and then it returns the math.square root of x times x plus y times y. Let's see, we need to import, math, and we need to import the logging system. Now, when we save this, it recreates the VMAG processor using this new definition. If we hit it with an input, let's see. We can see that it does the same thing. It logs the message here, 3, 4, those are the arguments, and then the output is 5. If we want to change the definition, we can do that too. Saving the code rebuilds the processor using the new definition. So what's going on here? When MFP is creating a patch element that you've just typed in the name of, it tries to find a factory matching the name of that processor. So every built-in processor like print or trigger or route or whatever has a Python class associated with the name. If there isn't a built-in, then MFP tries to automatically wrap an existing Python function. To do that, it tries to evaluate the name directly as a Python binding. So this lets us use many Python functions as MFP processors with no special support. You notice over here, we used math.sqrt to calculate the square root. That's just directly using the Python math library function. It's not defined anywhere in the MFP code base to, specifically. In this case, if we define a function in the custom code for VMAG, then that name is available to the Python auto wrapper, so it's able to use that as the guts of the processor. Custom code has another use too. Definitions that you make there can be used by name in the argument list of the processor or as literal data, as well as the name. So like we look, for example, at this trigger processor. Trigger copies its input to its outputs, doing some optional type conversions, and it has this set of single letter type specifiers that are used to state, like compactly, what the types of the outputs are going to be. So B is for bang, meaning any input will be just converted to a bang and sent to the corresponding output. There's also A for any, which means do no conversion, S for string, F for float, I for integer, so on. Those single letters are evaluated as Python code. They're just functions that are defined locally in the trigger processor that take one argument, which is the value, and they convert it to the specified type. So what if we want to add another type converter to trigger? We can do that in custom code by just defining a new function to convert the type and giving it a single letter name. So like, let's say we want to define a new conversion type for Boolean. There's not one predefined. And we can't use B because B is already in use by bang, but let's say we'll call it T for truth value. So we say def T, it takes a value as input, and it returns the Boolean of that value, right? We save this with the trigger processor, and now it didn't change anything visibly, but now we can use T as a type specifier for this trigger processor. And this new outlet, the third outlet, is going to always spit out a Boolean value for its input. So the examples so far have been of message processing code, but you can also write custom code to do DSP signal processing. Since Python isn't really appropriate for real-time signal code, I've embedded the Faust language with a special Faust twiddle processor. You can load Faust DSP code from files that you've edited offline, or you can live code it just like we did with Python. So when we create the Faust twiddle object with no arguments, it has no code associated with it, so it doesn't have any signal inputs or outputs. If we open the custom code editor, we can just write a Faust program into a string variable called Faust code. I'm going to make it a Python format string because we're going to want to substitute in a variable here, and just use this triple quote multi-line format so we can just embed the Faust pretty directly. So we're going to use a nice Moog ladder filter. So it's in standard Faust.lib. We're going to make a variable for the cutoff frequency. And you can see that by the curly brackets, this is where we're substituting a Python variable in. app.samplerate is the MFP sample rate. That's because the cutoff in the Moog ladder filter is on the scale is from 0 to 1, so it needs to be normalized by the sample rate so that you can use an actual frequency for the value instead of just 0 to 1. And finally, we define the process call, which is basically the main entry point for a Faust program. And now we click save. And what happens? Okay, now look. So now the Faust code has been sent to an LLVM, like just-in-time compiler, and the MFP wrapper extracts info about that Faust process's inputs and outputs, and then puts them on the controller here. So here we have one audio input, one audio output, and two message inputs for the cutoff and the cue parameters. So if we connect this up to a noise source, so we can monitor the signal. So now we should be running our noise through this filter, and like we'll just set up a slider for the frequency from from 20 hertz or 20 hertz to 2000 hertz, and we'll connect that to the cutoff, and then the cue will make another slider that'll go from 0.707 to to 10. That's not the full range of the control, but that's all I think we want. It's going to be useful. And let's see what it sounds like. So you can hear the frequency sweeping. If we make the cue higher, we can hear the frequency sweeping a little bit more clearly, right? So in addition to typing in the Faust in the custom code box, you can also pass like a very short one-line Faust program via like a code equals keyword argument here to the box itself, or if you have it in a file, you could pass it as a file with a file name equals keyword argument to Faust that would load code from that file before it's evaluated. Finally, if you want to dig down into the lower levels of MFP, you have an opportunity to run your own Python code at startup time. And you can use this to code up completely new processor types the same way that the built-ins are coded, which is as subclasses of the internal processor type. At startup, MFP looks for a file called mfprc.py. It's in the .mfp directory of your home directory. This Python file is executed in the main process environment, and it can do whatever you want. So in order to define a new kind of processor like we do in this example, the minimum you need to do are these things. First, you need to make a new class, and it inherits from processor. You can import processor from mfp.processor. You need to override two methods, the init method, which just at minimum needs to have this call to processor.init that adds these two arguments to specify the number of inputs and outputs that the processor has. In this case, it has one input and one output. And you need to override the trigger method. This is what's actually called whenever the hot inlet is hit on the processor. In this case, it logs a message and then it copies its first inlet to its first outlet. So it's just a no-op pass-through that logs a message. So you might use this for debugging. That's why it's called DBG. Now, if we save this, this processor will be available the next time we run MFP as DBG. This register line actually connects the name DBG to the class. So let's give it a try. Okay, so if we create a DBG processor, look, it creates just fine. And if we print its output and then send it something nice, we see that on the console output here, we get the message that we logged in the definition of the processor, and then the print processor prints that output, so we know that it's passing through whatever came to its input. Hope you enjoyed this video. These features are all in the master branch of MFP as of March 2025, but some of them are not yet in a tagged release. With luck, I'll release version 0.8 pretty soon with all these features included in it. Thanks.